video, we're going to discuss L'Hopital's rule. Now, sometimes you might see an S between the O and the P. That is not pronounced hospital like it appears. It is pronounced L'Hopital's rule. L'Hopital was a French mathematician, and he discovered a way to help us find the limits faster, more efficiently. And I always have students come up to me and say, well, why didn't you show this to begin with? If it's faster, if it's more efficient, why didn't we use this when we did limits to begin with? Well, to use L'Hopital's rule, we're going to have to rely on derivatives. And remember, we can't find a derivative without a limit. But then we're saying, hey, we can find the limits more efficiently through derivatives. So kind of an interesting little paradox here we have. Well, now we do have the skills necessary to find a derivative, right? So we couldn't do this initially. We couldn't do this before we found derivatives. But now that we know how derivatives work, L'Hopital's rule will make our derivatives a little bit easier, or our limits rather, a little bit easier to find. So let's just start by defining it. Suppose f of a is equal to g of a is equal to 0. F and g are both differentiable functions on some open interval containing that point a. And at g prime, the derivative is not equal to 0 except for at x is equal to 0, which we defined initially, right? That g of a is equal to 0. Then the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime, assuming the limits exist. Now I'm actually going to start by calculating a limit the old-fashioned way. So let's say we have the limit as x goes to 1 of, we'll take x squared plus 2x minus 3 over x minus 1. Now, first thing we always do with limit, and this does not change, this is very important. If we want to find a limit, the first thing we do is we plug in, always, because L'Hopital's rule only works if both these functions are equal to 0. So I'm going to plug in. I get 1 plus 2 minus 3, that gives me a 0 on top. I get a 1 minus 1 on the bottom, that's a 0 on the bottom. That is very important, that is not going to change. If we plug in and we get an answer, our answer is what it is. We don't have to do anything else. So before, what we said to do next is we would factor this. We have a polynomial over polynomial, and so we can factor x minus 1, x plus 3 over x minus 1. If we multiply it back together, we'd have 3x minus x give us 2x, and then negative 1 times 3 obviously is negative 3. And so then the next thing we're going to do is cancel out those factors that match the x minus 1s. Left with an x plus 3. And now we can just plug that 1 in directly, and we get 1 plus 3, which is equal to a 4. And that's our answer. We can still solve these limits that way, right? That's fine, that doesn't change. But let's apply L'Hopital's. Let's see how this speeds us up. So taking the same problem, first step is still to plug in the 1. We get 0 over 0. That is important to see. Then L'Hopital's rule says we can take the derivative of the numerator and of the denominator independently. Really pay attention. We are not saying here we're taking the derivative of the entire function. We're taking the derivative of the numerator, and then we're taking the derivative of the denominator. We're not having to use the quotient rule here. So we take the derivative of the numerator, we would get a 2x plus 2. We take the derivative of the denominator, and we get a 1. If I plug in that 1 right now, we don't get 0 over 0. I know that because I see that there's a 1 in the denominator. So I am just going to plug in. We have 2 times 1 plus 2. And that once again gives us 4. Notice we saved ourselves a couple of lines here. And this really wasn't a very hard problem initially. This was a pretty easy problem to factor. Remember the types of problems that we saw where we had to use multiplying by the complex conjugate, not the complex, sorry, just conjugate, the square root problems. We had to multiply by the conjugate. We had to sometimes simplify fractions and fractions. We had to use our sine x over x equals 1 if we're taking the limit of that. So these problems got a lot harder. Still, even in this easy problem, we saved ourselves a line of work, turned into a very simple problem. I'm not going to do the formal proof of L'Hopital in this video. You can find that on your own. But I'm going to give you the idea for why it works. We are plugging in. We're trying to figure out what the top goes to. We're trying to figure out what the bottom goes to. They're going to 0, both of them, right? But as we've talked about before, things going to 0 doesn't mean that they're going there at the same rate. We can't simply just cancel out the zeros and say it's equal to 1. That's obviously not true, because one might be going there a little bit faster than the other. Same thing was true when we saw that functions were going to infinity over infinity. We said that infinities aren't all equal, and so that's not just a 1, they're getting there potentially at different rates. So if we want to see how they're getting there at different rates, what we're doing is canceling off those factors of the same, and we're seeing what drives it a little bit faster. Or we could do it now through slopes, because we understand that derivative just a slope. So if I know that they're going to 0 over 0, I want to see how are we getting there? Who's getting there faster? By looking at the slopes, that is giving us that information. And so that's why L'Hopital's rule works. That is why we can look at just the derivatives. Let's take some other examples. Let's say that we have the limit as x goes to 0 of sine x times x over 3x squared. So this one would be one that we'd have to do a little bit more work on if we were going to apply our old ideas to it. If we're going to obviously cancel out an x here, and then we'd have the sine x over x. Now, first step is always to plug in. So if we plug in our 0, we get 0 clearly over 0. And that tells me it is an indeterminate form. We have to do more work to it. Now, just because we have L'Hopital's rule doesn't mean I'm going to jump into that first. Obviously, the numerator would require a product rule. As I said just a second ago, the much faster first step would still be just to cancel out an x. That makes it a much faster problem, even if I'm going to use L'Hopital's rule where I have to use my product rule. So we don't want to forget our old skills. We're just applying something new to it, or we're adding in a new idea as well. So now, if we wanted to apply L'Hopital's rule, we could have the limit as x goes to 0, cosine x over 3. And now at this point, we can plug in that 0, and we're going to get 1 over 3, and that will be our limit. This one wasn't a real hard one to see that sine x over x formation. We are going to get the 1/3, so I don't know that we really saved any time here by using L'Hopital's, but we can see that we can do it either way. Let's take another example. Let's take the limit as x heads to a 1, x minus 1 over natural log of x minus sine pi x. Now this one would be much harder if we didn't have L'Hopital's rule. If we look at this, I don't see any clear way of manipulating. And the first thing I should do, I'm kind of jumping ahead because I know I'm giving you something in indeterminate form. I should plug in the 1. So I get 1 minus 1, which is 0, over natural log of 1 is 0, and then sine of 0 is 0. So we get 0 over 0. That is always my first step. I need to make that clear. That is always my first step. But from here, I'd be kind of stuck. This is a much harder problem. I don't know of a clear way to factor it. I could definitely try to work on getting that sine x over x, but that's going to make other things messier too. So I'm not saying we wouldn't get there, but it is a harder problem than the previous ones. Now that we do have L'Hopital's rule, I see I have that 0 over 0 format. So I'm going to take the derivative of the top, take the derivative of the bottom. I take the derivative of the top. The derivative of the top is just a 1. I'm already guaranteed not to get a 0 over 0 in the entire fraction. Then we're going to take the derivative of the natural log of x. That is 1 over x. I take the derivative of sine pi x. Derivative of sine is cosine. And then I also have to multiply it by the derivative of the inner function, which is just pi. So we get 1 over x minus pi cosine pi x. So now let's see what happens when we plug in our 1. Get 1 over 1 minus pi cosine of pi times the 1. And cosine of pi is just a -1. And so when we multiply the -1 to the pi, we get 1 over 1 plus pi. And that's our answer. Now, it is important to note that L'Hopital's only applies to having 0 over 0. So obviously, if I gave you something like this, the limit as x goes to 2 of x plus 1 over x plus 3, there's no reason to use L'Hopital's, right? If I plug in that 2 right away, we get 3 over 5, and that's my answer. So we don't want to just automatically assume if I see a limit, I have to use L'Hopital's. You guys know me by now. You know I'm going to throw 1 or 2 in there that aren't possible to use L'Hopital because I want to make sure we're testing this first. I want to make sure that we are plugging in these numbers, seeing that we're getting that 0 over 0, or we see that we don't get that 0 over 0. If I had tried to use L'Hopitals, which I should not, I would get the limit as x goes to 2 of 1 over 1, which would tell me it's 1. That is absolutely false. I shouldn't have been comparing their slopes because it wasn't going to 0 over 0. It was going to some other number entirely. There is one other case where L'Hopitals will work. If we have the limit as x goes to some value, c, of f of x over g of x, right? And f of x and g of x are both going to infinity, meaning we get the indeterminate form infinity over infinity. This is another indeterminate form. Indeterminate form, remember, 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 over infinity, infinity over 0. A lot of different forms of it. The only one L'Hopital's explicitly mentions is 0 over 0. But let's think about why I could solve this as well. Well, I can write fractions, not just in terms of division, but multiplication by the reciprocal. So I could write this as 1 over g of x over 1 over f of x, which, if we were to think about this as multiplying by the reciprocal, we'd have 1 over g of x times f of x, which give us f of x over g of x. But because the f and g were both going to infinity, that means this fraction as a whole is going to 0, this one is going to 0. So notice this is just of the form 0 over 0. That is something that L'Hopital deals with. We just had to kind of view it in terms of the fractions. Now, the key to the trick to this is we don't actually have to do that. Once we show that it does work, we don't need to do that again. So let's say that we have 3x squared minus 2x plus 1 over 5x squared plus 4. If I were to plug in my infinity, I see that's going to infinity over infinity. So as we just discussed, this could be rewritten in a form of 0 over 0, but I'm not going to bother to do that. I'm just going to jump right into finding my derivatives. It's much easier to find a derivative when we don't have those fractions. So I take the derivative of the numerator, it is a 6x minus 2. I take the derivative of the denominator, which is 10x. So now if I plug in my infinities, I still get infinity over infinity. Well, I can do it again. I can take the derivative of the numerator, which is 6. I can take the derivative of the denominator, which is 10. And now I end up at something that is not just infinity over infinity, or 0 over 0. It's 6 over 10, which I can simplify to 3/5. So here we did two things different. One, we took something that was in the form of infinity over infinity, and we used L'Hopitals on that. Because infinity over infinity, L'Hopital can handle that the same way it can handle 0 over 0. The other thing that was different here is we had two steps of having to use L'Hopital's rule. We did it once, we ended up at a fraction that was still infinity over infinity. We did it again. Remember, L'Hopital's rule defined the rule when the numerator denominator went to 0, and also when the function in the denominator was differentiable everywhere except for maybe where the derivative of the denominator was equal to 0. Still could handle those points as x headed to a certain value. We can use L'Hopital's rule as many times as we need to. As long as we're getting that 0 over 0 or the infinity over infinity, we can continue to apply L'Hopital's rule. Let's take another example. The limit as x heads to 0 of cosine squared x minus cosine x over x squared. If I plug in my 0, I get 1 minus 1, which is 0, over 0. And so I'm going to use L'Hopital's rule. The derivative of cosine squared is 2 cosine x times negative sine x. And the derivative of negative cosine x is a negative sine x, turns it back into a positive. In the denominator, the derivative of x squared is 2x. If I plug in my 0, I get 0 plus 0, which is 0, over 0. And so I'm going to apply L'Hopital's again. Here I have to use a product rule. So the derivative of cosine is, once again, negative sine. Turns that back to positive, and it would be a sine squared. Then I have to add to that, but really it's subtraction, so minus 2 cosine. The derivative of sine is cosine, so I get a cosine squared. And then the derivative sign here is a cosine. And in the denominator, I get just a 2. At this point, I'm guaranteed not to get 0 over 0 because I do see I have something other than 0 in the denominator. So I'm going to plug in my 0. Sine of 0 is 0. Cosine of 0 is 1. And then cosine of 0 again is 1 over a2. And so we get 0 minus 2 plus 1, that's a negative 1 over 2, or a negative 1/2. So this one we did apply L'Hopital's rule twice over, and we ended back up at a limit value. We could actually get a limit value on this one. So we can apply the L'Hopital's rule. We can apply that as many times as we need to. Now there might be points where we just don't see that we're getting anywhere. And in those cases, we might have to look for another path forward. We can't use L'Hopital's on every single problem. Sometimes we do need to think about other ways to approach the problem. Let's do another example where we can't necessarily apply L'Hopital's right away. Let's do an example where we can't necessarily apply L'Hopital's right away. Let's take the limit as x heads to 0. I'm going to specify from the right, of cosecant x minus cotangent x plus cosine x. So if I were to plug in my 0 right now, cosecant of 0 from the right, well, if we think about cosecant, that's sine, that's heading to a positive infinity. And then we have cotangent, that's going to infinity as well, so we get infinity minus infinity plus 1. Well, right here, there's our indeterminate form, infinity minus infinity. But that's not a form that L'Hopital's deals with. So I need to think about something else I can do first. Well, I know that I can write cosecant as 1 over sine. I can write cotangent as cosine over sine. And cosine's just cosine, but that really wasn't a problem to begin with. Remember, that was equal to the 1, and that's fine. We can find that limit right away. So let me break this into two different limits. Let's take the limit as x heads to 0 from the right. And I'm going to put these together as one fraction, 1 minus cosine x over sine x. And I'm going to write the other limit separately because, again, that cosine wasn't causing me problems. I can do that right away. And so now I have this in a form that goes to 0 over 0, which means on this first limit I can apply L'Hopital's. This second limit was going to 1 to begin with, so I can just go ahead and say it goes to 1. I don't need to apply, and I don't want to apply L'Hopital's there. So I have the limit as x goes to 0 from the right. I take the derivative of the numerator, the derivative of 1 is 0, the derivative of negative cosine is sine, and then the derivative of sine is cosine. We already said that this limit was just equal to a 1. Now if I plug in my 0, sine of 0 is 0, cosine of 0 is 1, so we get 0 plus 1, which is just equal to a 1. And so we started with the problem that we couldn't apply L'Hopital's to directly because it wasn't in the correct indeterminate form, but by taking breaking it up a little bit and rearranging it, rewriting it in several ways, we were able to get to something that we could use L'Hopital's and we can solve for. I'm going to do one last type of problem, which is another indeterminate form that L'Hopital's doesn't deal with directly, but we can work it into a form that we can use L'Hopital's rule. So let's take the following example. So we have the limit as x goes to, we'll go to e from the right of the natural log of x to the 1 over x minus e power. So if I think about plugging this in right now, I have the natural log of e, which is just 1, to the 1 over 0 power. That is 1 to the infinity, essentially. This is called an indeterminate power. Clearly not in the 0 over 0 format and not in the infinity over infinity format the L'Hopital's can deal with directly. And why do we need to do something else to this? Because it seems like it's just going to 1 to the infinity. I think 1 to any power is equal to 1, right? But no, because remember, we're saying we're getting really, really close to it. We're not getting there entirely, which is the reason that all of these limits work, right? It's a reason that we can take something that's 0 over 0 and find a limit value. We're looking at where it trends doesn't actually reach these values. So we're never actually reaching e. We're never actually reaching 1 down here in the base. We have things very close. So we might have, we're approaching it from the right, so maybe 1.1 or 1.01 or things that are gonna get bigger as we raise them to powers, especially as that thing goes to infinity. So then the question becomes, is it getting to 1 fast enough? Is it gonna stay 1, or is the power getting large so fast it's gonna drive this number away from 1? So what I'm gonna do is rely on some exponents and logarithmic properties. I know, as a little bit of a side note here, that if I have e to the natural log of x, that is simply equal to x. I'm going to use that kind of in a reverse way. I'm going to take something simple like x, and I'm going to expand it out using this idea right here. So I'm going to take the limit as x goes to e from the right. I'm going to create this base of e, which means I have to create a natural log on top of it, of the natural log of x to the 1 over x minus e power. And that I should make clear that x minus e is all in the denominator of that exponent. And so this seems like I made the problem a whole lot more complicated, but why did I do this? Well, remember, if we have the natural log, we are always allowed to bring the exponent down to the front of that natural log. So we have the limit as x goes to e from the right of e to the 1 over x minus e times the natural log of the natural log of x. And I should point out before that exponent was on the entire natural log, not just on the x, and that's why we couldn't bring the exponent to the front first. It has to be the exponent on the thing we're taking the natural log of. So now, I still don't have it quite in that 0 over 0 format, but if I notice, if I kind of ignore or if I bring this limit inside of my exponential, I'll leave the e there as my base. I'm going to just concentrate on taking the limit of the exponent on that e. Well, then I do have that 0 over 0 format. Let me write it completely as a fraction. So we can take that natural log of the natural log of x, put in the numerator. And so now if we plug in the e, we have the natural log of e, which is equal to 0. Is equal to 1. Natural log of 1 is 0. We get 0 up here. And the denominator, e minus e, of course, is 0. So what I'm going to do is I'm just going to concentrate on this exponent. I'm going to leave the e off for a minute, and you'll see that this is what the book does too. The book does it a little bit earlier. The book just kind of does it right away. It says just take the natural log of the thing and then we'll stick an e on it afterwards. But this is the idea behind it. I'm creating that base of e so that I can take the natural log, which allows me to bring the exponent to the front, and then that exponent becomes something that is in that 0 over 0 format. So now inside that blue box, let's continue working with that limit. So we're taking the limit as x goes to e from the right. I take the derivative of the numerator. The derivative of the natural log is 1 over the interior, which is the natural log of x, times the derivative of the natural log of x is 1 over x, all over. Then I take the derivative of the denominator. The derivative of the denominator is just a 1 minus 0, or 1. And so now if we plug in the e, let's see what we get. 1 over the natural log of e is just 1. Then we have 1 over e here, and then in the denominator we have just a 1. And so we have 1 minus 1 over e as the limit of just the exponent. So remember, this was all going to be placed on that e. So for our final answer, it is e to the 1 minus 1 over e power, and that is our limit for this initial problem that we start with right here. So indeterminate powers, kind of a little different. We're using L'Hopital's rule still, but we just have to get to it. We have to do a little bit of work up front. So we have to start by taking our problem, creating a base of e, which allows us to take the natural log and the exponent. That allows us to work with just the exponent, which is now in that 0 over 0 format, in that indeterminate format that L'Hopital's can deal with. And then hopefully we can get to our answer from there. So again, I will stress that when we're using L'Hopital's rule, anytime we are finding a limit, we better plug in the number first. We better see that we get 0 over 0. Anything else, or infinity over infinity. Anything else, L'Hopital's cannot work with. Sometimes we can rearrange that. We can massage the problem to get that infinity over infinity or 0 over 0 format. Sometimes we can't, and sometimes we just need to apply different ways of approaching the problem. Once we do get to the 0 over 0 or infinity over infinity format, we want to remember that we are taking just the derivative of the numerator and the derivative of the denominator separately. We're not trying to apply both at once.